Hello viewers, in today's session we are going to discuss an important and conceptual problem from definite integrals, and here we are going to solve this problem where we are given a function f of x that is equal to 1 over square root of x times the integral from pi by 4 to x, and here we have 4 sine t minus 3 times f prime of t dt, where x is greater than 0. Then we have to find f prime of pi by 4, right? So here we are going to make use of two important concepts. The first one is the Leibniz integral rule, and then we'll apply the product rule for differentiation, right? So let us see how we can easily find out the value of f prime of pi by 4 using these two concepts, right? So let us differentiate both sides with respect to x. So here we have d by dx of f of x, and then we have d by dx of 1 over root x, and then we have pi by 4 to x, and here we have 4 sine t and minus 3 times f prime of t, and here we have dt, right? Okay, now d by dx of f of x is simply f prime of x, right? And here we can see that we have the product of two functions, that is functions of x, right? So the first one is 1 over square root of x, and the other one is this integral, right? Because this integral is also a function of x, so we have to make use of the product rule for differentiation, that is d by dx of uv, that is the product of two functions u and v is given by u times here dv by dx, and then v and du by dx, right? So now we can now write 1 over square root of x, then the derivative of the integral pi by 4 to x, and then 4 sine t, and here we have 3 times f prime of t and dt, and then we have this integral that is from pi by 4 to x, and then we have 4 sine t minus 3 times f prime of t and dt, and the derivative of 1 over square root of x. So now let us solve these two terms one by one. So here we have 1 over square root of x, and then we have to find the derivative of this integral with respect to x. So to get the derivative of this integral with respect to x, we have to make use of Leibniz integral rule. So the Leibniz integral rule says that the derivative of this integral whose limits are some functions of x. Suppose the lower limit is u of x and the upper limit is v of x, and here we have a function, say f of t dt, then the derivative of this integral with respect to x is given by f of v of x, and then we find the derivative of v of x, that is v prime of x, then we have a negative sign, and then we replace this t by u of x, and we write here the derivative of u of x, that is u prime of x. So now if we compare this integral with this one, then u of x is given by pi by 4, which is a constant, right? So pi by 4 is a constant, and v of x is given by x, right? So if the lower limit, in this case the lower limit is a constant, that is pi by 4, so we can slightly modify Leibniz integral rule here. So we have d by dx of say a to v of x f of t dt, where the lower limit, that is u of x, is a constant, right? So in general, if we take u of x as a, which is a constant, and the upper limit is v of x, which is a function of x, then the derivative of this integral with respect to x is given by f of v of x, and here we have v prime of x, and here this term is 0 because here we have u prime of x, that is the derivative of u of x with respect to x, and if u of x is a constant, then this derivative is equal to 0. So we are left with only this term, right? Okay, so now let us apply this rule to this integral. So we have here f prime of x is given by 1 over root x, and then we have f of v of x. So for f of t we have this entire expression. So f of vx implies f of x, because here v of x is x, so we have simply a 4 sine x minus 3 times f prime of x, right? So first we replace all these t's by x, and then we find the derivative of x, that is v prime of x. So here we have x, and then we have this term, right? Now in the second term we can see that here we have this integral. Now if we look at this expression, that is f of x is equal to 1 over square root of x times this integral, then the value of this integral can be written as root x times f of x, because from this expression we can write pi by 4 to x and 4 sine t minus 3 times f prime of t dt is equal to root x times f of x. So taking the value of this integral as root x times f of x, we have now the derivative of 1 over square root of x, and the derivative of 1 over square root of x can be written as x raised to minus half here. Then we have minus half and x raised to minus 3 by 2, that is x raised to 3 over 2, which can also be written as minus half, and here we have x times square root of x, right? So here we can write the derivative of 1 over square root of x as minus 1 over 2x times square root of x. Okay, so now the derivative of f of x, that is f prime of x, is given by this expression. So now the derivative of x with respect to x is equal to 1. So now we can write f prime of x is equal to 4 sine x minus 3 times f prime of x divided by square root of x. This term is simply 1, and here this square root of x and square root of x get cancelled, and we are left with minus 1 over 2x, and here we have f of x, right? Okay, so now we can find out the value of f prime of pi by 4 from this expression, right? By taking x is equal to pi by 4 in this expression. So now we can write f prime of pi by 4, and that is equal to 4 times sine pi by 4. Then we have minus 3 times f prime of pi by 4 divided by square root of pi over 4. And here we have minus 1 over 2 times uh, pi by 4 and f of pi by 4, right? Okay, so now here we can easily see that in the left hand side we have f prime of pi by 4, and here also we have f prime of pi by 4. So let us take f prime of pi by 4 as say m, right? Just for convenience, so we can now write this expression as m is equal to 4 times sine pi by 4, that is 1 over square root of 2, and then we have 3m, because f prime of pi by 4 we are assuming it as m, and here in the denominator we have square root of pi over 2, and here this term is 0, right? Because see, here we have f of pi by 4, and if we take here x is equal to pi by 4, then we can see that both the limits become equal, right? So the lower limit is pi by 4, and when we take x is equal to pi by 4, then here also we have pi by 4. So when both the limits of integration are equal, then the integral is equal to 0, right? So f of pi by 4 is equal to 0 due to this property, that is integral from a to a f of x dx is equal to 0. So when the limits of integration are same, then the value of the integral is 0. So f of pi by 4 is equal to 0. So this expression, entire expression is equal to 0. So here we have 0. So now let us rearrange the terms here. So multiplying this m by root pi over 2, we can now write m root pi over 2, and this is equal to 4 over square root of 2 minus 3m. So taking minus 3m to the left hand side, we have m root pi over 2 plus 3m, that is equal to 4 over square root of 2, and taking m common here, we have root pi over 2 plus 3, right? And here if we rationalize the numerator and denominator by square root of 2, we have 4 root 2 over 2, right? So now we can write m, and here we have root pi plus 2 times 3 is 6 over 2, and here we have 2 times 2 is 4, so we have 2 root 2, right? So we have m times square root of pi plus 6, that is equal to 2 times 2 root 2 is 4 root 2. So m is equal to 4 root 2 divided by root pi plus 6, and we have assumed that m is equal to f prime of pi by 4. So f prime of pi by 4 has the value, that is 4 root 2 divided by square root of pi plus 6, right? So viewers, this is how by making use of the concept of Leibniz integral rule, we can find out the value of f prime of pi by 4, and the value of f prime of pi by 4 is equal to 4 times square root of 2 divided by square root of pi plus 6. Hello viewers, in today's session we are going to discuss another important problem from definite integrals, and in this session we are going to discuss this important problem where we are given a function f of x which is equal to the integral 0 to x e raised to t f of t dt plus e raised to x, and this function f of x is a differentiable function for all values of x belonging to the set of real numbers, and we have to find f of x, right? So here we are going to make use of the concept of Leibniz integral rule, right? So what we will do, will differentiate this expression both sides with respect to x using Leibniz integral rule. So let us first quickly see the statement of Leibniz rule, and then we'll apply the rule to this equation. So now consider an integral whose lower limit and upper limit are some functions of x. Suppose we have here a lower limit u of x and upper limit v of x, and here we have a function, say f of t and dt, right? Suppose we need to find out the derivative of this integral with respect to x. Then Leibniz integral rule says that first we'll replace this t by v of x, that is the upper limit. So here we have f of v of x, and then we multiply this term by the derivative of v of x, that is v prime of x. Then we have a negative sign, and then we replace this t by u of x. So we have f of u of x, and then we multiply this term by the derivative of u of x, right? Okay, so this is the Leibniz integral rule, and here we'll apply this rule to find out the derivative of these two sides, that is the left hand side and the right hand side, right? So here we'll slightly modify this rule, and let us consider u of x as 0 and v of x as x, right? Then this rule can be written like this, that is d by dx of the integral 0 to x, and then we have the function f of t dt, and then we write here f of v of x. So v of x is x, so here we have f of x, then the derivative of v of x, that is v prime of x, is d by dx of x, which is 1. So here we have simply 1. Then we have f of u of x, and u of x is 0, and the derivative of u of x, which is 0, is also 0. So u prime of x is 0, so here we have 0. So this term is 0, so we are left with only f of x, right? So now if we compare this integral with this one, then we can see that we have 0 to x, 0 to x, and our function f of t is given by e raised to t, and we have f of t, right? So now let us differentiate both sides. So we have a d by dx of f of x, and then we have d by dx of 0 to x e raised to t f of t and dt, and then here we have d by dx of e raised to x. Now this is simply f prime of x, and the derivative of this integral can be calculated by using this rule. So this is simply f of x, right? And replacing this t by f of x, we have simply here e raised to x and f of x. So replacing all these t's by x, right, using this result, and here we have the derivative of e raised to x as e raised to x. So f prime of x is equal to e raised to x times f of x plus e raised to x. So now this is a differential equation, right? So let us rearrange the terms, so we can now write f prime of x is equal to e raised to x times f of x plus 1. So taking e raised to x common, and now we can write f prime of x over f of x plus 1 is equal to e raised to x. right? So here we have separated the variables. So this is a differential equation of a variable separable form, right? Okay, so now let us make use of the notation that is f for f of x, and we can use the notation f prime for f prime of x. So here f prime of x can be written as simply f prime, and for f of x we can write simply f, and here we have plus 1, and here we have e raised to x, right? So let us integrate both sides with respect to x. So we can now write here f prime over f plus 1 dx, and here we have integral e raised to x dx, and c is the constant of integration. So now here we have f prime dx, right? So f prime is equal to df over dx, and this implies that df is equal to f prime dx. So replacing f prime dx by df, so we have integral df over f plus 1, and here we have the integral e raised to x, and c is the constant of integration, right? So now the integral df over f plus 1 is simply a log of f plus 1, right? Because here we know the result, that is integral dx over x plus a is equal to log of x plus a, right? So here we have e raised to x, and c is the constant of integration. So let us again replace this f by f of x. So we have natural log of f of x plus 1, and here we have e raised to x plus c. So now we have to find out the value of this constant of integration c by using some initial condition, right? So let us make use of this expression. Now if we replace here x by 0, then we have f of 0 is equal to the integral 0 to 0, and here we have e raised to t f of t dt plus e raised to 0, right? So what we have done here, we have replaced this x by 0. So taking x is equal to 0 in this expression, we have f of 0 is equal to this one, right? So f of 0 is equal to 0 because the value of this integral is 0. Here the lower limit and the upper limit both are 0, right? And here e raised to 0 is simply 1. So we have obtained the condition, that is f of 0 is equal to 1. So when x is equal to 0, then f of 0 is equal to 1. So let us make use of this condition or information to find out the value of this c. So here taking x is equal to 0, we have natural log of f of 0 plus 1, and here we have e raised to 0 plus c. Now f of 0 is 1, so we have natural log of 1 plus 1, and here e raised to 0 is 1, and this is natural log of 2, this is 1 plus c. So c is equal to natural log of 2 minus 1, right? So we have obtained the value of c as the natural log of 2 minus 1. So let us substitute it in this equation. So we will write now natural log of f of x plus 1 is equal to e raised to x plus log of 2 minus 1. So now raising both these sides to the power of e, that is the exponential number. So we have e raised to natural log of f of x plus 1, and here we have e raised to x plus natural log of 2 minus 1. And we know that e raised to a natural log of f of x plus 1 is simply f of x plus 1, and here we have e raised to x minus 1, and here we have natural log of 2. So here we have used this result, that is e raised to log of say a is equal to a, right? Okay, so now we can write f of x is equal to e raised to x minus 1, and here we have the positive natural log of 2, so we can now write here e raised to natural log of 2, so using the laws of exponents. And then we can take this plus 1 to the right hand side, that is minus 1. So we have f of x and e raised to x minus 1, and here e raised to natural log of 2 can be written as simply 2 using this result. So here the value of a is 2, right? And here we have minus 1, so we can now write f of x is equal to 2 times taking this 2 in front of this expression. So we have 2 times e raised to x minus 1, and here we have minus 1, right? So viewers, the value of or the form of the function that is f of x is given by this expression. So this is how, by making use of this Leibniz integral rule, we can easily solve these kind of problems.